One is called MNOS memory element. MNOS memory element. So this is for achieving both electrical programmability and erasability. Okay. In MNOS, the conventional MOS structure was modified as follows. You know that this is the nMOS. P. Now the dielectric here consists of two parts. The gate dielectric consists of two parts in MNOS. The full word MNOS, the expansion of that is metal nitride oxide semiconductor. It's called metal nitride oxide semiconductor. FET. That is actually an MNOS FET. Okay. Here, therefore, the gate dielectric is not uniformly at oxide. Rather, just at the interface, there is a gate dielectric, which is a very thin silicon dioxide. Very thin SiO2, on the top of which there is a relatively thick silicon nitride. Thicker Si3N4, okay, thicker nitride. And on the top I have a gate material which may be metal or polysilicon. This is the gate electrode. Gate electrode. Okay, and you have got the conventional things for, you know, that for connection. So this is oxide, this is oxide. So you have got some metal here for connection purpose. So this is a metal connection. As usual, this is source, this is drain, and this is your gate. Therefore, you see that the only difference which this particular MOSFET has with respect to the conventional N-channel MOSFET is that its dielectric consists of two parts. The gate dielectric consists of two parts. The dielectric film which is in contact with silicon is a very thin silicon dioxide, extremely high quality. This is grown by thermal oxidation, dry thermal oxidation process. Thickness maybe is usually around 100 angstrom or even less. The thickness of this thing, this first initial the first film is 100 angstrom or less than that. Today's VLSI technology is considerably less than this. I am speaking of maybe slightly outdated things. If you compare the today's world, you know that even the total gate oxide thickness is around 200 angstrom. So this should be around 50 angstrom, 40 angstrom of that order. And the other one, the thicker silicon is at least 5 times thicker, roughly around 5 times, 2 to 5 times thicker. Okay? Then you have the gate electrode like this. In this case, what happens, you know, because silicon nitride has got a much higher dielectric constant compared to silicon dioxide. Silicon nitride dielectric constant is kappa is equal to 8. In this case, this is equal to 4. So nearly double. nearly double. As a result, it can be shown that though this oxide, the oxide on the top, the dielectric on the top, that means the nitride is thicker, its capacitance will not be that high as but this one definitely will be less than this, but still one can say that this oxide capacitance, the field effect, the electric field distribution in the oxide and nitride, there will be a very strong electric field in this oxide because the dielectric constant here is large, this compared to this one. This happens due to the boundary, you know that the boundary theorems, the dielectric boundaries, what happens in the dielectric boundaries, and as a result of that, what will happen, whatever voltage you are applying at the gate, this will cause an electric field. The electric field will be relatively much higher in the oxide compared to the nitride. The electric field which will be resulting because of the applied voltage at the gate with respect to the source or substrate will be considerably higher in the oxide compared to the nitride. And as a result, what is going to happen? You see that both things have been satisfied. The oxide is very thin, less than 100 angstrom, firstly. And secondly, within the oxide, there is a lot of electric field, which may be of the order of around megavolt per centimeter, just of the order of megavolt per centimeter. And that will cause, as I told you, that tunneling, because this is so, the barrier is so thin, and there is a strong electric field inside, there will be tunneling of carriers from the substrate into the dielectric. So if you are, because you have applied a gate bias, which is positive usually for nMOS, electrons will be tunneled from the substrate, in fact from the inversion layer, it may be so, from the substrate to into the dielectric. Okay, and in the interface between the two dielectrics, it can be shown that there are a lot of traps present. In the interface between the two dielectrics, there will be a lot of traps in the energy gap, in the band gap. And as a result, these electrons which are injected from the semiconductor into the dielectric by the process of tunneling, most of them will be trapped in the interface. That means if you now remove this voltage, these electrons will be almost permanently stored in the interface and will result in a change of threshold voltage. In fact, I can design this transistor in the same way as I discussed earlier. I can design it to be operating in depletion mode, so that it is on normally. But with the application of a momentary gate bias, again I have to apply the gate bias, relatively high value of gate bias, which is to be applied in the form of a single controlled width pulse or a bunch of pulses, a burst of pulses of total duration which is necessary for changing the threshold voltage. Okay, and that will result into a negative charge layer located very close to the interface, and that will repel subsequently the electrons which were accumulated in the inversion layer and turning the device off, as discussed earlier. So what I have done here, I have been able to make the device off from on state by applying a voltage at the gate. But this voltage, please remember, is not the usual voltage. It is relatively high voltage. So I have to provide some lines into the circuit to apply relatively high voltage, maybe of the order of 30 volt, 25 to 30 volt, for a very short duration. The duration, etc., has to be adjusted, that the manufacturer specification according to the operation. I want a reliable on and reliable off. That's important. So I have to, so that the device gets turned on or off, from on to off, if I apply a high voltage here for a very short duration. You now just reverse the polarity of this bias from positive to a similar negative voltage for almost a similar duration. If I had applied 25 volt plus here, now let me apply minus 25 volt. If I applied it for 50 microsecond, let me apply again for another 50 microsecond. Then what is going to happen? Again, by reverse tunneling process, the electrons, whatever stored in the interface, they will be removed and it will come back to the original state. So again, a transition from on to off or off to on. So you can, at your will, change the state, the conducting state of the transistor from on to off or off to on simply by applying a large short duration pulse at the gate of appropriate polarity. Positive bias will cause something and negative cause voltage bias will cause something opposite. So that way, this was the first kind of memory element which was developed. It is totally electrically programmable and electrically erasable. Both are possible. You have electrical programmability, as well as erasability. In the same device structure. Therefore, what I can do is the same way, wherever I have connected the polyfuse, almost similar configuration in series with the transistors, I can connect them, and this one can be turned on or off according to whatever signal I apply from outside. Therefore, it can be naturally you cannot expect the kind of packing density which is achievable in ordinary ROM. Do you expect? If you had used that, it is more or less in the programmable, the fuse link kind of things, that in place of diode you connect. The problem is this has to handle a lot of power. Therefore, I have to always use in the same way as we have used the ROM. So in series with the driver transistor at each node, whatever I have, I told that the ROM of MOS ROM is nothing but is equivalent to the AND plane of a PLA, which I discussed in the last class. So at each node, I have a MOSFET. In series with the MOSFET, I have to connect such a device. So naturally, I am achieving programmability and erasability, but at the cost of more space. EPROM cannot, till today, EPROM has got limitations of packing density. Whereas normal ROM can have very, very high packing density. That has to be remembered. But why, you know that today's erasable, today's EPROM, this kind of MNOS type of devices are not popular. In fact, it is not there at all. Today's commercial EPROM, whatever is available to you, if you just ask the manufacturer what kind of device we have used here, they will say it is definitely not MNOS. MNOS was popular at very, but there are many. Problem of MNOS is to create a very good interface and life. MNOS deteriorates faster than the other kind of EPROM which I will be discussing just now. So this one is still, it was an important research component. It was also commercialized. It has got still some applications, but because the other device has got superior features, which I'll be discussing now, it has been almost fully replaced by the other kind of devices known as floating gate EPROM. This is not floating gate. The other kind is called floating gate EPROM. So I am just showing only the device. Here, it is more or less similar to the first device, the FAMOS, but there are two gates. Let us see what is it. Sorry, you have to have some metallization on the top of it. As I told you, this is drain, this is source, and there are two gates now. This gate is a floating gate. And this gate, which has got an external connection, is called control gate. So this is the device. Both the gates are usually polysilicon. Usually N plus poly, but there may be variations. Heavily doped poly, both the gates are. This one is true for every, I have not shown sometimes, but you please remember the source and substrate normally are shorted, and they are shorted through a butted contact. This kind of contact is called butted contact. You see that the P plus contact is just adjacent to merging with the N plus diffusion. That is intentionally done. It will come, I think we could not have scope for discussing the other details. In fact, one can show that the CMOS latch-up can be controlled more appropriately if you have a butted contact rather than a separated contact. You know, you have to take a contact from the substrate, all right? And if you keep a distance, a large distance between that contact and the N plus source, the probability of latch-up is more. One can show. Let us not go into the device details, but that is why this contact, whether I have used this particular terminology earlier, I do not know, but this is a very common terminology in MOS. This is called butted joint or butted contact. So anyway, you see here, I have a very thin oxide as before. This oxide, the first oxide is very thin. This is an ultra thin silicon dioxide. Thickness may be even of the order of 50 angstrom. Depending on the technology, initially it was around 100 angstrom. As I told you, it has become almost close to, or sometimes even less than 50 angstrom of that order. Whereas the other oxide may be around 100, 200 angstrom. This oxide, that is a typical gate oxide. And you see that after the formation of the two gates by two poly, this is called two poly system. You know that not today, normally the MOS, any MOS or CMOS technology is described in terms of two poly, two metal, two poly, one metal, two metal, one poly, etc. This is an example. Normally in this case we have to use two poly levels, and then at least one metal or after two metal. That depends on the complexity of the VLSI circuit. So this is a two poly system. The first poly level is for the creation of the floating gate, whereas second poly level is for the creation of this gate, the control gate, and all other gates. All other gates of NMOS, PMOS, whatever may be in the circuit. Okay, because the thickness here is typically of the order, total thickness from here to here is just of the order of the gate oxide thickness, which is normally used. Now what happens here just before, this floating gate is totally covered by oxide, as I told you in the case of FAMOS. But in the case of FAMOS, there was no connection from the gate. You remember that there was only single gate in the FAMOS. It was totally shielded by oxide. But in this case, the floating gate is totally shielded. There is no external connection. It's totally shielded in all sides by very, very high quality silicon dioxide with a very high resistivity in excess of 10 to the power 14 ohm centimeter. I told you. Let me reiterate. And then the second gate, though in the diagram I have shown that this is also sealed, but there must be some connection, because never we take the connection just over the device. We take the connection laterally over the thick oxide or field oxide. So it is not that this gate is accessible. There is a connection, but this gate is not accessible. It is totally shielded. And here also the same thing is going to happen. We don't use MNOS. Everything is oxide. Now, if we apply a high voltage here again for a short time, that will induce a strong field, because this oxide is much thicker. This one is thick, and this is very thin. So there are two capacitances in series, and there will be a strong field created at this oxide, and because it is so thin that the tunneling transmission probability may be considerably higher. So by the same process, electrons may be tunneled from the substrate into the floating gate, or tunneled back from the floating gate into the substrate by the application of a suitable gate bias at the control gate. Floating gate is shielded, but control gate you have to apply a suitable bias here. Tunneling, sometimes you know that to affect the tunneling more appropriately, we also do it through the drain also. We apply now, what is the polarity of drain bias we apply? Positive. So this junction is reverse bias, there is a strong field here. There is a strong field here. Okay. If we apply a large gate bias here, then in this region, in the overlap region, there will be still stronger field. And that will again cause the injection of carriers, avalanche, because in this, if I apply a drain bias, both, but this is not really primarily based on the avalanche multiplication, but this may be helped by application of drain bias and control gate bias. One can really accelerate the process of tunneling in this particular case as compared to the earlier one. And similarly, by applying a reverse voltage, I can remove the carriers from this. This is what is known as floating gate EPROM, which is very popular today. In all EPROM technology, whatever you are seeing, commercially available products, they use this floating gate EPROM. Again, the problem of space, all these things are that they never expect that EPROM will have a higher density than a PROM. PROM is very dense. That is why in calculator chips, etc., whatever you know, the most of the stored data, they are kept in commercial, because calculators are used in billions. So one can produce such ROMs in billions. There is a very good market for it. Therefore, you can make. But for many specialized applications, we need repeated change in the storage. And this kind of device is very good, but we cannot afford a very high packing density in this particular case. Packing density is limited. People are trying to innovate technology, but this is a real problem. That is why I told you the other concept has come. Instead of using this kind of things, you can use a RAM with a backup battery. It works in the same way. Backup battery, one problem is that after some time, that the battery may be discharged and you are in trouble. Therefore, there should be some arrangement so that the battery, either in a very reliable thing, there should be arrangement for that automatic monitoring and replacement of battery without disconnection. Replacement of battery without any disconnection. Otherwise, if there is a disconnection for a short time, everything will go. Those arrangements are there. People have done that kind of arrangement. But this is now a very popular thing in automation and other applications where I have to store certain information for a considerable length of time. And there, this RAM, ordinary RAM, a very high density RAM, you can use for that kind of application. But wherever in the laboratory or many other applications in computer, you need a short time data storage, then EPROM is a very good alternative to that. So this is, in short, the programmable ROM. Whatever I have discussed for the programmable ROM, that's it. But as you know, that the static RAM is a so-called volatile RAMs, which you have studied, I'm sure, to quite a good extent in your earlier courses. That is a very popular kind of memory element for in-process, online memory. It works only when during the battery is on. When the power supply is on, it loses all the power. And static RAM, that kind of RAM, that there is one first called static RAM, ordinary latches, permanent latches, or static RAM. We shall see that it does not give you high density. For each memory element, you need at least 6 transistors. For each memory element, you need at least 6 transistors. Therefore, people try to innovate, and they develop the so-called dynamic RAM. And today's dynamic RAM operates, each element comprises only 1 transistor and 1 capacitor. So static RAM is the most convenient because it is independent of any clock frequency, But dynamic RAM needs a clock and refreshing, as you know that. And static RAM, therefore, it's very most welcome memory so far as volatile memory applications are concerned are static RAM. But because of its limitations so far as packing density is concerned, people go for dynamic RAM. There is no other reason. Dynamic RAM has come simply because of high packing density and more complexity, etc. There is no other reason. But for your information, the people have been able to innovate technology. Even static RAMs with very, very high capacity has been already announced and marketed, and Japanese are dominating in this particular field over US. Anyway, though it has been stopped, but I will just start with static RAM. Static random access memory. You can access any memory element randomly. That's why the name random access memory. The basic memory cell is like this. This you have studied, I'm sure. There are 2 latches. There is one single latch, 2 inverters connected back to back. This may be shorted or in fact. I'm sure you have studied this basic static RAM in your earlier course. Here you see that what I have really done is this is a column. This is one column of a full RAM. Please remember, this is one column of a RAM chip, one column of a static RAM chip, in which I have shown only one element. So of the entire column, I have shown only one element. So this is the latch-up element, the memory, basic memory element. In fact, including these two transistors, I should have shown, but I'm showing. But please remember, the basic memory element also includes these two transistors. Each element has to, each location must have these two transistors. Therefore, there are 6 transistors per element. 1, 2, 3, 4 for the latch circuit, and 5, 6 for connecting the X address to the latch. You see that if I make X high and Y high, and X1 and Y1, it means you have addressing, you have access to the particular memory element. X is a particular row. There are hundreds of such rows. I have shown only one row. And this so-called Y is a column, a signal which is being provided to each column, a signal which is provided to each row through X, and each column to Y. If X is 1 and Y is 1, it means that you have gone to the intersection of the part. I can write it as Xm and Yn. So there are X1, X2, X3, etc. So now there are Y1, Y2, Y3, etc. So particular Mn. So this element is located at the intersection of mth row and nth column. As I make X high and Y high, you have access, because these two transistors are on and these two transistors are on. Therefore, you have access to this particular memory element. Now what I do simply, if I want to write the memory, simply I turn W1. So this is for just memory access. And for write operation, I have to, along with X1, Y1, I have to make W1, but read 0. Complementary. Whenever W is 1, read is 0. It's called write and read. So the data is inputted through this line called bit line. This is bit, and this is bit inverse, bit bar. Normally the bit line is, used for writing, whereas bit inverse for readout. Okay? And all these bits finally form word. This is one bit of a full word. And as you make data apply, so what is going to happen? Simply this latch is on, and you do not know what is the state of, whenever, as soon as you make it on, this is a very simple kind of thing. We shall be discussing more complicated and more proper thing. Latch will be on, it may be either 1, 0 or 0, 1. It depends on you. It depends on the natures of something, what happened initially. So it may be 1, 0 or 0, 1, but it will be stable in that. Now suppose I apply data which is 1. And suppose it was 0, 1 initially, when you have made xm equal to 1. But because this is 1, there will be a change from 0 to 1, and it will be cumulatively, that's the process which happens. And therefore, each element should have intrinsically very high gain. The corresponding inverter should have very high gain if you want a high speed. That's an important thing. So naturally, very quickly, it was initially 0, 1, but it will become 1, 0, because you have addressed 1 in this line. Or if it was 1, 0, it will be 1, there is no problem. It will be done immediately. Suppose due to some reason, this was 1, 0, it was the previous state, and you are again applying 1 through this right, so 1 will 0 will be maintained, it will be an immediate process. But if it was otherwise 0, 1 initially, by applying 1, you have to change the state, it takes some time, and therefore there is a time involved in this writing process. some kind of writing time is involved, okay, called memory speed. One of the memory speed consists of many times. This is one contributing factor. How much time it takes to send a writing signal from here to here, and then to establish it to the particular 1-0 stable state or 0-1 stable state, whatever the case may be. And you are getting the inverse here. If you are interested to read it out, simply make R1 W0. Whenever you are interested in read out, of course you have to make, because otherwise there will be confusion. You don't do that. There should be complement. W and R are complementary signals. Okay. So you see that this is the column. So overall chip will consist of, suppose as I have written XM and YN. M is 100, N is 100. What does it mean? How many elements are there on the chip? 10,000, 10K. It is a 10 kilobit chip. Its capacity is 10 kilobit. If both of them are 100, means there are 1,000 memory elements located. So bit by bit, each individual memory element can be accessed, can be written, can be read out. That is why it is also called random access memory. That's a great advantage of this kind of thing. But problem starts, as we shall see just now. I think you know how to organize this memory, that I'm not drawing here. The same thing is repeated, same block. This is just one representative block in the MN intersection. You have to go on writing the blocks for the different elements in each column and similarly in each row and connect them to the same. You see that XM is the mth address line, X address line, and all it is connected to the corresponding memory elements. Similarly, YN is the nth Y address line, and the corresponding elements are present on this particular row. So this has to be kept in mind. But what is the problem in such kind of arrangement? What's the problem in such kind of arrangement? You know that I want a rapid access. I want to have a rapid writing time, rapid writing process. I also want to have a very rapid read out process. Because otherwise I cannot, I may have a very large capacity, it does not really benefit me if it is not compatible with my main logic processors, my CPU. It must correspond, otherwise I am in trouble. And do you envisage any problem in this particular circuit? You see that this bit line, as I said, is a very long line. I said that it is 100. 10 kilobit is a very simple example. You know that 64, and now recently, as I was mentioning, I found a paper where 2 megabit SRAM people are speaking of. 2 megabit SRAM. It's a very big thing. So you just imagine how long the line is. And this line provides connection to so many elements. Then what will be the total capacitance? Suppose all these transistors are off. All x's are 0. X1, X2, etc. All of them I have kept 0. Therefore, these circuits are not coming into picture. But the bit line itself is floating on an oxide, on silicon. And there is MOS capacitance, as well as junction capacitance. So each bit line will have substantial capacitance. Each bit line will have substantial capacitance. So you just see that when you are making Y high now, you are accessing one of the bit lines. Say in example, if Yn is 1, so this particular two pairs of the particular pair of bit lines are now accessed. Okay, let it be accessed. That means if I am willing, I can provide a signal in this path, or if I am willing, I can take out whatever signal was there from this path via these two switches. All right. Now suppose I make, due to some reason, the earlier thing was B was 0 and B bar was 1, just in the earlier stage. Now you are making data high 1 and W1. Should that will go? Suppose Xn is still kept 0. Do you think that 1 will be transmitted at this point immediately? will not be, because there will be a lot of capacitance involved in this line. Not only capacitance, but inductance, that also becomes important for very high frequency. There will be some delay involved for the signal from passing from this point to this point. Forget about the particular memory. Forget about the particular memory. If this is 0, this is both the transistors are off, just for the convey of signal from this point to, as you go down and down to the farther point, the delay will be still more. This is called transmission line delay. This is coming simply because of the relatively large capacitance. Line is quite long, and also inductance is there, and particularly for very high frequency, you have to consider in an RC. This line being quite long, there will be substantial R. So RC primarily important for frequencies up to a few hundreds of megahertz. Then LC becomes important above 500 megahertz as you go, but normally we are not speaking that. If you are remaining below 500 megahertz, it is RC delay which is usually more important than the LC delay. I think you have studied that in transmission lines. What is the characteristic impedance of transmission line? High frequency, root over L by C. R and G are not there. Why? Because they are not important. At high frequencies, omega L becomes very large, 1 upon omega C becomes very small. So both of them dominate over R and G. So, but if you are remaining at low frequency, what is the corresponding transmission? You have seen just the opposite. So something like that. This is a very important thing should be kept in mind. Whenever you are speaking of VLSI, the delays which we normally discuss, if you are remaining in frequency range about up to several hundred megahertz, it is the RC delay which is more important. But for extremely, that the so-called edge technology which people are now speaking of, the gigabit, etc., and their LC delays become gradually more and more important. That has to be remembered. For hundreds of megahertz, RC delays up to, whereas for up to gigabits, then LC delays come. So this is one component of delay associated. Then you see that you turn XM1. I have applied here 1, so this has now, by that time it has been established. I have given sufficient time for XM. Let us assume like that, so that this 1, 0 is established properly. Then you are now switching, this XM is turned on. Maybe it was 0, 1 in the earlier state. That is exactly that it was, as I told you. So again, this was also a finite time involved. This 0 to 1 switching will not be. And suppose before this in that case, this will become 1 and this will become 0. But I suppose I want to read out this, then therefore I expect that B bar should give you 0. But I want to expect this to be read out immediately. What do you mean by 0 here? Some voltage which is very close to 0 volt. What do you mean by 1 here? Some voltage which is very close to 5 volt or at least 4 volt. I suppose I want to, I am very, very, impatient man. I have designed a circuit, but I want to apply. I have not seen what is its capability, but I want to apply in a CPU which is very high-speed CPU. And I find it does not work. Then I want to analyze what is happening. Exactly that is going to happen here. If you want to do it, then before it has reached 0, you have make W 0 and read 1. And you will get something which is not the, maybe it does not fall within the noise margin. And it will not function properly. And that happens. So even if this particular thing, whatever I have discussed, if I want to operate at a high speed, then I will definitely encounter problem because of the bit lines. In fact, this memory element, individual memory element is so small that their charging and discharging time may be very fast. Individual memory element is extremely small one. The C's, etc. are so small that their charging and discharging may be very fast. It is the bit lines which become the actual culprit compared to the individual memory elements. Because they are sluggish, they are stored such lot of charge. You are trying to change them, that they do not change. So you have to do something that this charging and discharging can be done very fast. Again, I think I have past time. So I have stopped here today, but this is a very interesting. So if you want to understand memory, basic memory, what are the timings involved, how speedy the memory is, these things have to be important. Bit lines play a very thing. So I'll discuss in the next class.